Hi everyone. In this video, I would like to talk a little bit about the history of Dask. There are a lot of people who've been with Dask since the very beginning, half a decade ago, with Python for a decade. They know a lot of the accumulated history and heritage of all of these software projects. And there's lots of people who are coming in very new. They might be new developers, or might be in some other field. Maybe they're in sales or marketing. We at Coiled had our first company meeting just a couple weeks ago and realized that very few people actually understood the history of what we do, where we come from. So I want to make a video, not just for Coiled, but for everybody about what this project means to lots of people and who it serves and where it comes from. So it'll be a little bit about business, it'll be a little bit about community, and a little bit about technology and science. So you can't really understand Dask without understanding what's sometimes called the scientific Python stack, or SciPy, which was actually kind of renamed to PyData. There was an intentional choice to kind of remove science from the name because it started being used so much outside of science, but it really comes from scientific Python, and that's a good thing to keep in mind. So if you sort of walk back a little bit in time, there were a few different competing software technology stacks that were used in business or in science, in any kind of computing. There were a lot of corporate stacks. So think Oracle, SAS. You don't hear about these much today, but they're still very much in use. And these were, a decade ago, these were dominant. These were in every major company, and they were doing most processing. These were super well trusted, but they were also pretty inflexible. You couldn't do lots of novel things with them. They also were really expensive. Then there was Python, right? And Python was kind of this ragtag team of people who were making really expressive, really exciting algorithms, but weren't really designed for businesses or for enterprise. Python didn't scale, but at the time, no one really cared. No one was working on big data. And then a little bit after that came Hadoop and sort of the whole Spark space. And this is an interesting blend of the two because it was both open source, but it was really much more corporate open source. And I think they really made that transition to enterprise a lot better than Python did. So they were really dominant in the business space. But if you go back, 5 to 10 years, there's a big open question about which technology stack would dominate or which would become more popular. If you sort of drill in a little bit to business users, it's worth recognizing or remembering that there really wasn't interactive data science software. This wasn't a thing. People used Excel, which I'm guessing most people have seen before. And there are people who use databases to do more custom queries on larger data sets. And then there were also professional software engineers who wrote, Fortran, C++, Java. But there really wasn't this middle role of someone who knew a bit of programming, but really focused on the business side or really focused on the technology side, really focused on some other thing that wasn't programming. There was no sort of journeyman programmer. On the scientific side, there was also the same. We had theorists, we had experimentalists who knew how to build physical machines, but none of these groups really thought too much about programming. There were also computational scientists who were, again, professional software engineers who wrote in Fortran and CUDA and C++. But there's this big chasm in between those two groups. And then that chasm started getting filled by languages like MATLAB, IDL, Mathematica, R, Python. And these languages were easy to use so that semi-trained programmers could use them, but also very effective. And this produced a whole range of productivity in science. And I think R and Python generally became dominant in that space, and eventually I think Python kind of beat out R. And these were highly productive systems that allowed scientists to be very, very good at their jobs, much better than they were able to do before. Then when data science came around, something interesting happened, and this whole stack of interactive, high productivity languages shifted into the business world. And this is kind of, I think, why Python was successful, is because it sort of grew up in the scientific world. And a scientist is actually a pretty good proxy for a data scientist. And so there was a decade or 2 decades of product development and marketing and all these things that we now think of today. They were already done in Python. And there was a really mature technology stack that could solve a lot of really critical business problems in the data science machine learning space. So that's how a bunch of open science folks came to rule the world. It's worth noting that a lot of the Python developers at this time weren't professional programmers. So Jupyter, for example, was created by a quantum physicist and a neuroscientist. NumPy was made by a researcher at the Mayo Clinic. If you talk to any software engineer in the Python space who's a maintainer, who's above about the age of 30, ask them what their PhD is in. They almost certainly have a PhD, and it's almost certainly in something that's not computer science. More often geophysics or biology or astronomy. I did some astronomy work, and I also did a lot of forecasting about how weather forecasts affected our power grid, especially with renewable energies. That's my personal background. I gave up that research along with everyone else who's in this stack. We all realized we're having much more impact providing software for all of the other scientists in the world and all the other business leaders in the world to have their own impact. So Python really came to fill in this gap in between database users and professional software engineers. And that gap is of growing importance today. Additionally, Hadoop and Spark also started filling in that gap, slightly closer to the software development side. They're more commonly used in data engineering workloads, but it's still adjacent. And so Python and Spark are kind of in this space together. People generally preferred Python. It was easier to use, it allows for more creativity, a little more expressivity. But clusters and distributed hardware, Hadoop and Spark were really the winning stack there. And so there's a question in the Python community, can we scale Python? Is that something that we can do? Can we take our existing ecosystem of packages and react to the growing needs of big data and the presence of Spark in our space? I and many others were working at Anaconda at the time. So if you wanted Python support at the time in the Python stack, you went to either Anaconda or Enthought. Anaconda used to be called Continuum also. So those three names are kind of consulting companies that were really, really popular at the time. Anaconda has then since grown to be a product company. They do lots of really cool, exciting things today. You should go and check them out if you don't know them already. Anaconda was investing in Python. They saw Spark as a threat and they wanted to create a big data solution. And so they decided to make Blaze, which had a lot of really exciting ideas, compiled code, optimized expressions, big data computation. It's a whole new paradigm of computing that had a lot of high potential impact. I worked on Blaze for a while, so did many others. It didn't actually succeed that well. I think it failed to gain traction. In my mind, it's because it was too ambitious. It tried to invent too much. And so existing Python users, it just felt foreign to them. We really need to be more Python native and more PyData native. And so this was, I think, a good learning experience for all of us to not try to reinvent, but to try to enhance the existing community. And so out of Blaze, I then and others started a project called Dask, which was actually a side project. I actually started Dask, the first commit was during Christmas vacation, 6 or 7 years ago. And Dask was very, very small in scope. This was designed as a reaction to Blaze. We wanted to make a parallel version of NumPy for gridded data that worked on a single machine but operated on larger than memory data sets. We copied the existing user experience from NumPy. We tried not to reinvent anything. We also heavily relied on the existing code of NumPy to do the actual in-memory computations. It's like rather than create a new body, we just created a skeleton and then kind of like pasted muscles and skin from other projects. It was kind of a Frankenstein of a project. But it allowed us to be really productive really quickly and a lot of really good user feedback very early on. Generally, a good solution for any product today. The first application of Dask was really in gridded data analysis. So there were many fields that had big data, but they didn't look like the sort of tabular data sets you see in a database or Spark. So in lots of business applications, you've got a table of data with rows and columns. And if your data doesn't fit into that space, it's actually really awkward to use as technologies. Dask was able, by leveraging NumPy, to handle these very large data sets that had this different shape to them. And we see a lot of effects of the history today. We see Dask used in medical imaging, in geospatial imaging, in simulation analysis, and energy, in NASA. And so this really came out of this sort of first group of users that were using single machines with 50, 100 gigabyte data sets on the laptops. And we were really successful there because of a partner technology project called Xray, which is coming out at about the same time. And Xray put Dask inside of Xray. And this actually gave us an early user base that was really well served by the Xray community. So Xray served as sort of that frontline support troops for all of their users creating examples, good marketing, good documentation. And then we were there to provide more computational expertise. This was actually a really good lesson for us in Dask. Rather than trying to reinvent everything and make our own technology stack, we learned how to partner well with other technology, other open source technologies. And so today, zooming to the future a little bit, or to the present, most Dask usage is indirect. It's through some of these other software projects. So Xray, Prefect, Rapids, XGBoost, and there are others, right? So most growth today in Dask is also indirect. And so as we think as Dask maintainers about how to grow the system, we think about how to identify and support successful partners. So for example, there's a lot of work today happening in statistical genomics. It's sort of on the boundary of should we invest time or not invest time. There's a lot of activity happening in life sciences. How do we have the greatest impact there? And so we try to identify these partners and support them to the best that we can. So going back to history, so we had this big gridded NumPy thing. It was serving all of these, non-traditional big data use cases and having a lot of really good impact. And we shifted, as one would expect, also towards tabular data sets. Many people use pandas. Then, today, in the future, pandas is going to be around. And people wanted a big pandas data frame. So just like how we did with NumPy, we parallelized pandas. This is arguably a much larger business opportunity. It's also a lot more competition and noise in this space. And so we were sort of hesitant to get into this space, but we're just pulled by all the demand. So this accounted for about only half of Dask's use. We expected everyone to want big NumPy and big pandas. And that ended up not being the case. So almost all of our actual early customers weren't in that category. They wanted something else. Python users quickly hacked the internals of Dask to build it into their own systems. So just like how I mentioned Dask is really good with partnering with other technology products, other open source products, individuals saw that and said, oh, I can use this inside of my own code. And so I say this often, please forgive me if you've heard this before, but it's as though we had built a nice car and all users wanted was actually the engine in that car. They ripped out the engine and put it into their own rocket ship that they were building, or their own Roomba, or some other thing they're building. In general, the Python space is more creative than the sort of Hadoop Spark space or than the Oracle space. People in Python build weird stuff. And Dask ended up fitting into that weirdness category pretty well. And so our first customers actually were a bunch of hedge funds and banks who had built some internal complex task scheduling system inside their organization and wanted to leverage Dask instead because Dask was frankly better than what they had internally. So at this time, I personally moved to New York because I was following a girlfriend at the time. But it was a good place to build a software consulting practice. And so I actually knocked on lots of doors of hedge funds and banks in Manhattan and sort of gave a nice demo. I actually gained a lot of respect for the sales process at that time. And that's why, again, a lot of Dask's larger users today, Capital One, D. Shaw, most large banks, most hedge funds, if you have a credit card in your wallet, there's a decent chance that the credit risk model on that credit card was calculated with Dask at some point. But that's why these are a lot of our bigger customers, is because of this history of just me physically being in New York City at the time. As an example, here's a credit risk model. And so this image is what we show to show how Dask is not MapReduce, it's not Spark. Spark and MapReduce were really good at things that were really regular. You're going to do the same operation, lots of data, then you're going to do a shuffle, then you're going to aggregate all those things together. And Dask was good for way more custom, way more weird computations that come up a lot in finance, because finance is a complicated field. And that come up a lot today in machine learning too. This is a good proxy for what machine learning looks like today. So we kind of stayed in this state for a couple of years. We would find support contracts, either in finance or in the government, to build out different capabilities of Dask. And we just grew. We were listening to users and growing Dask in a nice, organic way. This is in contrast to maybe how a lot of open source gets built today, with sort of VC-funded startups doing sort of high-growth things that are really hype-driven. Dask was much more community-focused and much more user-focused. We were very pragmatic during this period. We were running consulting services shop for, half a decade. However, at the same time, large tech companies started getting more into Python and more money started pouring into the space. That was interesting. It's very good for sustainability, but also changes the nature of the game a little bit. So this is about the era of, Google's creating TensorFlow, PyTorch is Facebook is supporting PyTorch a lot. The clouds are making their own products. And Nvidia started getting very excited about the Python space. This is a picture of Jensen Huang, the Nvidia CEO, at a keynote stage of Nvidia's annual main conference, talking about Dask. This was a weird thing to see. I was still at Anaconda at the time. Nvidia wanted to build out their own GPU data science stack. They wanted a distributed framework, and Dask was flexible enough to support all their GPU needs. So I actually moved over to Nvidia. We had an existing team at Anaconda. There were lots of other distributed Dask developers and other companies. We made sort of a second large home for Dask maintainers at Nvidia under sort of the Rapids banner. I worked here for about a year and had a great time. Nvidia's an interesting place to work. So we had these sort of walk back a little bit in time to our earlier part of the presentation. There are these three competing software stacks, sort of traditional enterprise stack like Oracle, the Hadoop stack, and this Python stack. And by and large, Python is one. I mean, certainly Spark is still very present, and certainly Oracle and SAS are still around. But Python is where the excitement is. That's where the growth is. That's where the users are. If you look at Spark, they're really trying to get more into the Python space. But the Python space has also changed a lot, right? We've added really advanced machine learning. All the big tech companies are here now. All the clouds are here. And so it's this really weird mix of sort of this ragtag scientific community-driven group where sort of the Dask folks come from, and a ton of money and trillion-dollar companies. And it's weird that we're on equal footing. And so just culturally and socially, it's a weird situation. We made Coiled to try to present our view of Dask and our view of scalable Python open source computing in this more competitive and more supercharged space of big data science, machine learning, AI. So that's what we're here to do. We're here to make lots of customers happy and serve their needs, but we're also here to preserve those values that we came in with, much like companies like Anaconda have done throughout the last decade. We're very happy to follow in that tradition. So that's the end of history. I'm actually going to talk a little bit, just very briefly, about all of the Dask work that happens and how I sort of bucket it into different categories. This might help you understand some of the things that are happening, help you sort of give a framework for those activities. So these are my arbitrary buckets, but I think a bucket one is workflow. So these are all questions that users ask when they encounter Dask. And I think they ask these questions in order. So the first, can I actually solve my kinds of problems with Dask, right? If I want to handle streaming data, does Dask do that for me? Is there a way to do that? If I want to access a lot of satellite imagery, can Dask do that for me? If I just want to rip data out of Parquet and train an XGBoost model, can Dask do that for me? And so mostly the work that happens here in the Dask space is in Dask adjacent projects. And mostly the Dask maintainers are supporting those other groups. Then there's a question about deployment. So once I've figured out that Dask solves my problem, I've experimented locally on my laptop, I now need 100 machines to run this, or 1,000 machines to run this. How do I get those machines? This has been actually probably the focus of a lot of the Dask maintainers over the last couple of years. It's also Coiled's product. So maybe 2/3 of Coiled's engineers work on solving this problem, mapping cloud infrastructure to Dask workers in as efficient and safe and secure and cheap a way as possible. It's a really hard problem. I think we're doing a pretty good job at it. It's an interesting product. Quick sales pitch, go check out Coiled. Once you have those machines and you start scaling up, you start asking the question, well, does it actually do what's promised, right? Or do things fail? Or given that things are going to fail because the user is going to screw up, Dask is going to screw up, the cloud is going to screw up, how do I make sure that it fails in a way that I can understand? And so a lot of the Dask team at Coiled is actually focused very much on this problem, making sure that the Dask is as stable as possible and as comfortable an experience as possible when it does fail for users. I personally am sort of slightly one step ahead, and I'm doing a lot of proofs of concept around performance today. So how do we, once things are running smoothly, I start scaling up, I start running this not in an experimental way, but I start running it every hour. Suddenly I care a lot more about performance, I care a lot more about costs. And so how do we make Dask faster? Not just Dask, but all the community projects around Dask. And that's an interesting challenge for not just the Dask team, but again, everybody. We work really hard with the Nvidia team, with folks like Numba, folks like Pandas, Arrow, to try to make the entire stack more efficient, which is critical as this stuff grows larger in size. And then finally, once you're successful at this level with Dask at scale, you tend to want to share it with your colleagues. And this can take many different forms. I think this is a place where I think we need to get better at. I think Dask actually has way more use than people realize. It does way more stuff than people realize. And I think communicating all of those capabilities to everybody is critical. So that's why I think I make videos like these. And thank you all for hopefully making your own. So that's it. Thank you for your time. Hopefully this video gave you a little bit about the context of Dask and the scientific Python stack. I really like that our roots are in science. I think that actually brings a lot to the current culture around Dask and Coiled. We really value transparent and open communication. We really value technical excellence and really value a sense of community and being kind and thoughtful about each other. We're also finally mission driven. We're not here to make software. We're here to solve actual real problems that are important to the world. So that's it. Thank you again for your time, and I'll see you around.